Welcome back to the third and final session of Statistical Thinking for Forensic Practitioners, a CSAFE short course sponsored by NIST. Dr. Hal Stern from the University of California, Irvine is with us again to close out this three-part series. Hal, I'll turn it over to you.
Great. Good morning, afternoon, evening, depending on where you are. It's good to be back. This is the third session of the short course Statistical Thinking for Forensic Practitioners. We usually start with a get to know you minute or two. And so I'm going to have Anthony pull up the questions so we can kind of learn where people are, what your job is. And there is a third question a few pages down on what forensic discipline you work on or with. And so if you could take a short time to let us know, that's helpful and helps me as I go through this a little bit. We have 2 hours today, and the focus today is on taking the probability and statistics from the last 2 weeks and applying them with more of a laser focus on the actual analysis, interpretation, and reporting of forensic evidence. Okay, Anthony, do you want to give us our results? As has been the case for the previous 2 sessions, we are pretty evenly spread across the US. A small number of people, only 1 reporting in Europe, 2 more exciting places, don't know what they might be, and almost all forensic practitioners. And then you should be able to page through these as well. Friction Ridge is by far the largest group, and a few other of the pattern and trace disciplines. So I'm going to close that and get going for today. So you can see the outline. The things I'm hoping to cover today are to think about basically 3 different approaches to the analysis, interpretation, and reporting of forensic evidence. What I consider the status quo in pattern evidence, and as you all know by now, CSAFE is really funded to focus on pattern and digital evidence. So that will be kind of where I focus a lot of attention, but the things I say apply more broadly. So thinking of forensic examiners as providing expert opinion, and then a couple of more quantitative approaches, one that is known as the 2-stage approach, and one is the likelihood ratio. And hopefully in the course of the 2 hours, we'll cover the strengths and limitations. I start with a very, very quick overview of the previous 2 sessions. If you were not at the previous 2 sessions, this won't get you very far, but it should get you the key takeaways that I'm kind of going to rely on as I speak today. For the first session 3 weeks ago was on probability, and we talked about probabilities as numbers between 0 and 1 that describe the certainty about something happening. And we spent some time talking about the fact that probability depends on information you may be assuming, and that will come up quite a bit today. And probability distributions will come up when we try to talk about building likelihood ratios. It requires us to be able to talk about how likely certain measurements are under different scenarios. The statistics piece, which was just last week, is focused on what we call statistical inference, taking some data and drawing conclusions about a population. And that includes estimates and confidence intervals and hypothesis tests. So we talked about those, and of those, it's really hypothesis tests that will come up as we talk about the 2-stage procedures. So that's a very quick review. The next handful of slides are going to go quick because they're things I think by and large you know, and they are not the main topic of the short course. I use some of these slides on occasion to do an overview and maybe introduce forensic practice to people, but this group knows about forensic practice. So I'm focusing much of the discussion today on the source conclusion issue. That is, we have evidence from a crime scene and a suspect, one typically known source, one typically questioned source. And I write the evidence as E, and we have 2 hypotheses. One S, that the items from the crime scene and the suspect come from the same source. So S is for same source. And not S means different source. Mathematically, that sometimes gets written as an S with a bar over it, but I won't do that very often. It'll generally say not S, and it may even say D for different source. And so that's our goal for the most part today. And this is the piece that goes a little fast, right? Lots of different evidence types, lots of different issues to think about. The role of the Dalberg standard, again, something I think you're all familiar with, so I won't belabor it. But to me, this slide basically just reinforces, along with the NRC report and the PCAST report, the need for us to be thinking about reliability and uncertainty in the statements we make about the evidence. Whoops. Again, a quick slide. This is how I think about it. We're looking at the evidence. We identify similarities and differences. In case there are any new people here, I'm not a forensic practitioner, never have been. I have sat with forensic practitioners and spent a lot of time talking to them. And what I described here is consistent with what I've learned there. That we all kind of agree we should be looking at the evidence, both the physical evidence and the measurements that we make on the physical evidence to assess the observed similarities and differences and try to decide how likely they are if the objects came from the same source and a different source. And so when you say, how should we do this task? It turns out there have been a number of articles written that try to describe different strategies. Researchers tend to slice the world up in different ways. I slice it up the way you see here. I'm going to talk about 3 approaches. 1, expert assessment based on experience, training, and accepted methods. Second method, the so-called 2-stage approach, which proceeds to analyze evidence in 2 stages. The first, trying to determine if the crime scene and suspect samples appear to be indistinguishable, match. We can think about different ways of describing that. And then the second stage to assess how likely it is to get a coincidental match. And then the third approach, the likelihood ratio and the Bayes factor. So with that having been said, here we go into the first of the 3. We'll talk about forensic conclusions as expert opinion. As Anthony said, if you have questions, you can just pop them into the Q&A. I have the window open, so I will see them. I won't stop whenever you do one, but I will keep my eye on it and figure out if I can integrate it in at some point or other. So what do I mean by forensic conclusion as expert opinion? The expert analyzes the evidence. They may have some measurements. They may be looking at features in the case of latent prints. And they are typically looking for similarities and differences. Often start by looking for differences. Are there reasons for me right off the top to know that these did not come from the same source? Some obvious feature that's in the known source that does not appear when it should in the question source, or items like that. And then again, this based on my conversations with practitioners, as more analysis goes on and there is no glaring difference, the weight of evidence begins to shift a little bit and they begin to see more and more similarities. And at the end of this analysis, we often get opinions reported as categorical conclusions. In latent prints, that often comes out as an exclusion, an identification, or a statement of inconclusive. There are some discussions and some movement in some disciplines towards multi-point categorical scales that would talk about there's some support for same source, there's strong support for same source, and the like. And as you all know, in some instances better than I, a lot of discussions in different disciplines on what should be allowed. That is, can we say there's strong support? Can we say it's an identification? Or can we only say more likely than not? As you all know, there's been a lot of pushback against phrases like to a degree of ballistic certainty, things like that, which are very, very difficult to interpret and don't appear justified. One point to make here, the categorical scales are fine as a way to proceed. I'll have some things to say about that, but we have to be a little careful about some of the ways conclusions are sometimes expressed. And in the document comparison world, there's a standard that identifies a 9-category scale that includes statements like the author of the known samples wrote the question sample, the equivalent of an identification, or it is highly probable that the author of the known samples wrote the question sample, or the author probably wrote the question sample, these kinds of statements. For those who were here back 3 weeks ago on the probability discussion, these kinds of statements themselves are logically problematic because they are talking about the hypothesis rather than the evidence. And I've tried to convey over the last two sessions that it's easy to think about probability being assigned to the measurements we make on the evidence or the features we see on the evidence. It is not, in my opinion, appropriate for examiners to be making probability statements about the hypothesis. And in this case, the hypothesis is, did the known source write the question samples? We can't do that without, as you saw, having a pre-evidence opinion about that question. And that in the Skipper et al. Case, and all the previous sessions are available so people can go back and the slides are available to see what I'm referring to. But you can't make a statement like this without having started with an opinion about whether it's the same source or not. And that is really the job of the trier effect. So I'll stop there. It will come up again later when we talk about likelihood ratios. There is one interesting note here. As I learned more from the document examiner community over the last 7-8 years, I learned that the standard was written based on what I would think of as kind of the two-stage approach. That is, the meaning of behind the people who wrote the standard was, when I say highly probably wrote the question sample, I mean the probability of seeing this degree of similarity if it's a different source is very low. But the way it got codified into the standard is, as I've described, problematic. So to understand the Daubert standard and the Frye standard both basically want us to make sure testimony is based on reliable principles and methods. I note here that reliable in its legal sense, and in some sense in the colloquial or conversational sense, means trustworthy. Statisticians and measurement scientists tend to think about reliability in a more formal mathematical sense. Again, something we talked about last time. Reliability means consistency of measurement, and validity for statisticians means accuracy. And so reliability to measure something well, validity to be accurate. And we talked last time about the fact that they're not the same thing. When we talk about reliability, we're really talking about if we do the measurements again or analyze the evidence again, would we get the same conclusion? And you can think about that in several ways that are laid out on this slide. One way is to say, if I gave you the same evidence a month later or 6 months later and asked you to do the analysis again, would you draw the same conclusion? We think about that as repeatability. Or we can ask, if I gave the same evidence to a different analyst in the same discipline, would they give the same conclusion? We think about that as reproducibility. And those are two kinds of reliability. Note that knowing hypothetically that all analysts would give the exact same conclusion, the process is incredibly reliable, does not yet say that everyone's giving the same answer and they're giving the correct answer. So that's why I emphasize reliability is different than accuracy. Reliability is, will everyone give the same answer? Accuracy is, do people give the right answer? And we saw last time, if people are all giving the right answer, then they must be reliable because they must all be giving the same answer. However, if they're all giving the same answer, they are definitely reliable. They may or may not be accurate. The relevance of reliability and validity have been drawn to the attention of the community in part by the PCAST report and its focus on black box studies. As a reminder, a black box study means that the examiner is basically being treated as a black box. The examiners are being given quote unquote cases, that is crime scene sample and suspect sample, where the experimenter knows the ground truth. And the examiner is being asked to give their response to the evidence. So that's the black box, is known samples in, analysis being done by examiner, and output out. And the PCAST report received a lot of attention. The authors recommended black box studies. The DOJ in January of this year issued a response saying black box studies should not be required in the way the PCAST describes them. We talked about this last time a little bit. My argument is everything that PCAST said about black box studies was actually good experimental design principles. And therefore, it may be challenging to do what PCAST asked us to do, but it doesn't mean PCAST was wrong in what they said. And we just have to acknowledge that we can't necessarily do what PCAST said. And then the other challenge with black box studies is people have noted correctly that a black box study really speaks to the discipline, but does not necessarily speak to any one case. And that is for sure true. But I always end up back at the point where I say, black box studies are useful. A friend of mine, a colleague of mine, Jeff Salyers, is on the call, and he put a note in the Q&A box to clarify that the DOJ didn't necessarily really issue a response. It was the closing days of the Trump administration, and a quote unquote pre-decisional draft was placed on their website. So thank you for that clarification. So I talked briefly about black box studies. What kinds of statements come out of black box studies? The one that I think highly of, the latent print study that was published in the Proceedings of the National Academies of Science in 2011, carried out by Ulrich et al., Nobles, and the FBI. They found from that a false positive rate. That is, non-matching evidence was declared to be identification. So these are false identifications, and the percentage was around 0.15%, so a little bit more than 1 in 1,000. So that was really quite positive for the discipline. The interesting result was the false negative rate, which was 7.5%. So 7 out of 100 times mating pairs were identified as non-mates. So these are false exclusions, if you will. And no one's saying the study is perfect, but it's a good study. I think it's an example of why I like these kinds of studies. I think this is fascinating information. One of the things that I think everyone was surprised by was the high false negative rate. And a little bit of a reminder, this is going to come up a few times today. The false positive rate that they are reporting is the probability that there was an identification given, and remember, given means we're restricting to the population of cases where there are non-matching prints. The known print and the crime scene print do not match. We know that for a fact. We consider a set of such comparisons and look at the error rate. That's known as the false positive rate. Some studies look at the probability of non-mates given that the examiner makes an identification. Remember the distinction in how we think about conditional probability. If we restrict attention to the set of cases where an examiner makes an identification, we can look at all of those identification cases and see how many errors were made there. That is not the false positive rate. We'll come back to it a little bit later. They're different, and that's a key thing to remember is when you see these probabilities or when you hear someone describe an error rate, you need to pay very close attention to what the set of cases they are considering are. So here's a little bit of an amplification on that last point. The people who do diagnostic tests, like medical tests, here's a procedure, here's a medical test, it came back positive, do you have the disease? Look at a concept called the positive predictive value. The positive predictive value is if the test came back positive, drug test or COVID test, or in our case, if the examiner makes an identification, that is the examiner in the case is the diagnostic test, if they come back positive and say identification, we might ask, what's the probability that they really do match or that you really do have COVID? That's known as the positive predictive value of the test, or in this case, some forensic studies have been published where they let's look at all the times the examiner made an identification in my study and find out how often they got it wrong. You'll notice that that's one minus this positive predictive value. Sometimes that was the false discovery rate. So we have a false positive rate, non-matching pairs incorrectly identified as matching, and a false discovery rate, okay, an identification conclusion turning out to be wrong. The false positive rate is the traditional error rate. It's what PCAST wanted. When people think about the error rate of a test, they think about the false positive rate. That is, they think about doing a COVID test on a bunch of cases that do not have COVID and finding out how often they get a false positive. That's the traditional error rate. The other quantity, this false discovery rate, is not the one that people focus on. And the reason is a little bit technical, but the reason they don't focus on it is because the set of cases that are being looked at are a mix, right? These are cases where the examiner said ident, and it includes both cases that are true idents and cases that are not idents. That is, it includes true positives and false positives. And it turns out that it depends on the mix of those. So if I do a study and if I give the examiners a ton of matching pairs and very few non-matching pairs, then I'll have very few false discoveries because they have very few opportunities for false discovery. So this is probably the most confusing piece of today's course. So you may have to or want to go back and think about it again. But the error rates of primary interest are, think about a set of cases with known truth, known ground truth. They either match or and should be identified, or they don't match. We focus on one of those sets and look for false positives, false idents, or false exclusions. So let me go forward from there. Mention a few other results from the Ullery study on this slide, just in terms of repeatability and reproducibility. So you see the kinds of statements that get made. We look for repeated decisions, and again, in latent prints, the results were high, but again, maybe not as high as people would have imagined. And it's helpful to see that and to get these kind of data. I mentioned before, a challenge with black box studies is black box studies do a wide range of cases, and it's not clear how to take the results of a black box study and use them in court. One way that I think about this is I imagine that accuracy as well as reliability may well depend on the quality of the prints or the complexity of the signature. And one could imagine doing a series of black box tests for different types. And one place where this was done 20 years ago was in handwriting. And you can see that in high complexity cases, the accuracy was higher and there were fewer inconclusives than in medium complexity signatures. So not high complexity cases. Signatures with high complexity are easier to analyze, and they got more correct and fewer inconclusives. So that's the kind of way one could imagine validating and using expert opinion going forward. So a few final remarks on expert opinion. Information on the reliability and the accuracy of forensic analyses is, in my view, and hopefully yours as well, extremely helpful and should be and will be, I believe, increasingly expected. So that the black box studies and recently published one on bloodstain pattern analysis, and one has been carried out, I don't think it's been published yet, on footwear. I think this is really great. I just think the data is super interesting and something we can all learn from. As long as we remember the black box speaks to the field and not to a specific case, okay? And that we also need to be attentive to how, as the federal rules of evidence say, the method was applied in a specific case. And my last point on this slide is one I always like to emphasize is, what do we do, for example, about the fact that there are unique situations, right? We're not going to do black box studies about typewriters in this day and age when they're used so rarely. For me, that's okay, as long as when presenting evidence, we are appropriately cautious to say, the evidence that I see is consistent with the note having been typed on this typewriter, but we have to acknowledge the uncertainty about how many such typewriters are out there. So, so that's the end of the first little piece of today's session, forensic conclusion as expert opinion. I'm going to answer one question that came up in the Q&A. James asked, is a 1 in 1,000 false positive rate good enough to allow latent prints to be used to sentence someone to life in prison, to death? Where does a reasonable doubt come in? It's an excellent question. It's not one that a statistician by themselves can answer. That's one that society as a whole and our system gets to answer. For those who've been listening to me for two sessions plus, we need to acknowledge zero error rate is, generally speaking, not attainable in any of the things that we do. And so the way you phrase the question is a good way to phrase it. Is it good enough, right? Should we hold out for 1 in a million? Should we, we just have to recognize, as per the discussion last week, if we change the threshold, in this case, for expert opinion, the threshold is in someone's mind. If I change the threshold, I won't call it an ident unless I am so convinced that that error rate drops to 1 in a million. It means we're going to get more false negatives. And, that makes sense, but the trade-off between false positives and false negatives is inevitable. And it's one that we need to think about and figure out where we want to land. So thank you for asking the question. Excellent question. And Carl, thank you. Carl notes that one of the limitations of the studies is that it doesn't include the full lab practice in terms of the verification step or the technical reviews. And I think people are increasingly trying to do more realistic black box studies, for example, by integrating cases with known ground truth into lab practice without telling people, which begins to address that. So thank you both for putting your thoughts in. It really helps the session. So I'm going to move us forward to the next of first, we have our Zoom test yourself feature. So the slide and this pop-up say the same thing, so nothing's being blocked. One of the things that you have told me is I need to be quiet and give you time to read it and think about it. In this case, I ask which of the following statements are true and invite you to answer. So there are 60 people on. Please answer. It's more fun for all of us. I'm just making sure Anthony's awake.
I'm still here. We have 12 people who have voted. I am going to make a quick note, despite the fact that I'm not supposed to speak here, that we are going to run these polls a little bit faster today than we have the last two sessions. So I think most of them are true, false. Hopefully that helps them move along a little bit quicker. I'm going to give you about 10 more seconds.
Okay, Anthony, there you go. Thank you. So I'm going to close the box. Everybody thought the third one was true. And then the others were more of a mixed bag. So let's go through these in a little bit more detail. The first said, if a black box study finds high accuracy, then it must also be high reliability. And that is actually true, even though only a small percentage of you identified that. And the reason is accuracy means there's one correct answer. And if it's a black box study shows that all the examiners are getting the right answer, that implies they must agree. So that means they are, by definition, reliable. The flip, the second item, is not true because they could all agree, reliability, but be wrong. We hope that's not true, but it's in the realm of possibility. So reliability doesn't guarantee accuracy, but accuracy guarantees reliability. And then the third and fourth return to this somewhat confusing point. Not confusing because I didn't make it clear, let's be on the record, right? It's confusing just because it's a little challenging. False identification occurs when things we know don't actually match are incorrectly identified as coming from the same source. And that is, in fact, the definition of a false identification. And then the fourth item says, we can estimate the false identification rate by looking only at identifications and figuring out which ones get it wrong. And remember, this is what I call the false discovery rate, or 1 minus the positive predictive value. And that doesn't work because it depends on the mix of cases that people are seeing. So I'm going to leave that behind. Here's the second question. In carrying out a black box study, what do we do with inconclusives? This has been a somewhat controversial topic. People are writing papers about it. And I'm seeking your input about this. Remember, for this question as well, each one is you can pick more than one. So are these appropriate things to do with inconclusives? And people it's nice. This one's nice and in order. So the most people like the last one, and then half the people like the fourth, a third like the third. Thank you to those who are replying. Let's go through them one at a time, as we did. So I've repeated the questions here, and my answers in this case appear in parentheses after the end. Inconclusives are always errors because the pair must either be a same source or a different source pair. I'm with you. This does not appeal to me. Interestingly, though, several of my colleagues have written papers arguing that this is, in fact, the correct way to think about the world. Second item, inconclusives should always be marked as correct because they are not errors. I don't agree with this at all. And some early papers in the disciplines did this or seemed to do this. So that was not good. Inconclusive should be omitted. A third of the people said this. In concert with the fourth one, I think this is okay. That is, I think it's okay to focus on errors among decisions. But then I think if we're going to do that, we need to have more than one summary of the study. So you could imagine saying, what percentage of answers for this examiner were conclusive, one way or the other? That's a good piece of information to know. And among the ones that were conclusive, what was their error rate? That's another good piece of information to know. And we would not be excited about an examiner who only made decisions in 10% of cases. And that would come out in this way. And then we all like the idea of trying to design studies to include some cases where inconclusive is, if you will, the right answer. Another question has popped up, which is asked, is there a statistical manner in which subjectivity can be ascertained? That is, with handwriting analysis and signature identification, and in some of the other pattern disciplines, there's a lot of subjective analysis going on to decide if things are similar enough, if the loop looks enough alike. The black box studies are, if you will, the statistical approach to trying to get at that. Some of the OSAC groups have been talking about ways of allowing examiners themselves to try and allow for this degree of subjectivity to show up with some support, strong support, you know, to put in some degree of strength of their opinion. But it is a very tricky question and a very typical thing, a very difficult thing to quantify. Anonymous attendee, can we get a 10-second warning? Yes, we'll do that. Sorry. I think some people think of this as possible to make a mistake. Right. So someone is letting us know that inconclusives are sometimes not looked at as an error because obviously the most serious consequences accrue to real errors. I'm going to move on because there are other topics that I want to talk about today. So we can leave the questions there. Time permitting, we can come back to them. The second approach I wanted to discuss is what's known as the two-stage approach. It tries to break the forensic comparison problem into two steps. The first step, can we determine whether the crime scene sample and the known suspect sample agree on a set of characteristics? And that question is somewhat similar to the hypothesis test question we talked about last time. And if so, we would say the two samples are indistinguishable. Two samples can't be distinguished. We might say they match, although many people don't like that term. Stage two is then, given this match, we want to know how likely could that have happened by chance? Because if one way to think about this one is if we're judging eyewitness identification and the car color comes up and the eyewitness says the color of the car is white and then the suspect is found and has a white car. So they match, they're similar. But when we say identification, we would say, well, how likely is it to find an individual with a white car? That's pretty common. So stage two in that case would suggest the matching white car evidence, though it's similar, is not strongly indicative of an identification. This two-stage approach has a long history, and it's used in some disciplines. You can argue it's used in the glass evidence. But even in some of the pattern disciplines where expert opinion is what might be happening, my impression from conversations with the examiners, they often think about it in this way as well. So the two stages we're talking about for those reasons. For stage one, sometimes determining similarity is easy. That's true for categorical data like blood type or DNA. It's true for car color and eyewitness test. So in other cases where we have continuous measurements, like the chemical concentration of various elements in glass or the refractive index of glass, it's a little bit harder. You won't get an exact match because of the measurement process, but we could use a statistical procedure, as we discussed last time, to decide whether the two samples of glass fragments appear to have come from populations that have the same underlying concentration. I note here, and we'll talk a little bit more about it, one challenge with the two-stage approach is when we say that we can't distinguish, it blurs a number of situations. It blurs the case where the two situations appear to match perfectly, and we can't distinguish them, from the situation where they don't match, but they're close enough that we can't rule out that they came from the same source. And those just get treated exactly the same in the two-stage approach, and that one might think of as a problem. I'm not going to go through this slide in great detail. It's intended as a slide to remind you, those who were here last week, that the first step, the similarity, is basically a statistical test. That is, we have samples from a crime scene suspect. Think about a window at the crime scene. We have a bunch of fragments. We think about them as representing the crime scene window. We find a suspect. They have glass fragments on their sweater. That comes from some other source. We think about that sample as characterizing that other source. The statistical test allows us to say, under the null hypothesis that they came from the same source, how likely is it to see the differences that I see? And we need some decision threshold, the p-value, that allows us to decide whether we're going to say indistinguishable or can be distinguished. So that's the statistical test. And here's an example, again, not to go through in detail, but to show you that you might have 5 measurements of aluminum concentration in 2 different samples. In this case, they appear to overlap a fair bit. So we might say these probably could have come from the same source. They probably cannot be distinguished. And we find when we do the test that the p-value is quite high, which you'll remember means if they came from the same source, the kind of difference I see here would be expected. And that turns out in this case to be true. These did come from the same glass source. There are a lot of statistical procedures for doing this. That's all that this slide says. There are a number of ways that statisticians might critique the testing procedure here. I've laid them out here. When I talk to statistical audiences, I tend to spend a little bit more time on these. For you, it's merely to note that the statistical approach is reasonable, but there are assumptions being made and we should be thinking carefully about them. The statistician should. For me, the important thing for this workshop is not the technical concerns about the statistical test, but what I'll call the conceptual concerns. And there are 3 of those. The first is the role of the null hypothesis. You'll remember when we learned about the hypothesis test last week, the test does not treat the 2 hypotheses symmetrically. It assumes the null hypothesis is true until proven otherwise. And so that means in this case, what we traditionally in statistics call a type 1 error, rejecting the null hypothesis, here that turns out to be a false exclusion, right? Some people, and we said this in an earlier session, some people think of a type 1 error as a false positive, but that's not true here because it would not be a positive statement to say that these 2 samples don't match when they should have. That's not a positive outcome for society to let someone go. Right? The type 2 error is a false inclusion. So now you've said these are indistinguishable, but they really came from different glass sources. So now you've falsely included someone with incriminating evidence when you shouldn't have. And again, that doesn't seem like a false negative to me. So we want to avoid false positive, false negative terms in this setting and focus on false exclusions and false inclusion as our language. I would argue, and others have said this to me as well, we basically have the wrong starting point, don't we? We don't necessarily in forensics want to start by assuming the null hypothesis of same matching sources is true. We want to start by assuming they're distinguishable and then maybe get good enough evidence to reject that. So that's the first conceptual error or problem. The second conceptual problem is our reliance on a binary decision. So I hinted at that before, and it came up in one of the earlier questions. If there's a low threshold and we make it easy for the statistical test to reject, for us to exclude, that's one type of decision. Or if we have a high threshold and we accept the null, then we have lots of inclusions. And that can be problematic. Here's a picture that I hope helps everyone see this. Let's start with the left-hand side of the picture. I picked a threshold. The threshold is the goalpost here, the vertical bars. And I've got a measure of the difference between the two glass samples. The top is when I have same source glass samples, I expect to get a difference around 0 because they're same source. And I have this threshold, the black measurements, the measurements marked in black are false exclusions for that threshold. And the red corresponding to when I have different outcomes, I expect to see a non-zero difference. But in these red cases, I see a small difference and I decide these two samples may have come from the same source when they didn't. So those are the false inclusion errors. So notice that I picked a threshold and I have a certain level of false exclusions and a certain level of false inclusions. And then what I did is I changed it. I said, let's lower the threshold. What happens? More exclusions, fewer inclusions. So you can see in this graph the trade-off when we make a threshold. We were earlier asked about the 1 in 1,000 error rate. Is that are examiners using the right threshold in their mind if we accept that error rate? You can see that pictorially here. We need to pick a threshold and choose whether we want to accept more false exclusions or more false inclusions. So that binary threshold is really important. And the third conceptual challenge is when we separate into two stages, we may stop at the end of stage 1 when in fact we would have been better off going on. And this is an issue that's also been coming up in medicine and other disciplines. When you rely on statistical tests, as we do in stage 1 here, you can make two different kinds of errors. You can say you reject the null hypothesis, in this case, excluding someone, when the null was true, and that's problematic. Or, you may exclude someone and wish you had, or vice versa. And as this is not a unique issue. So a couple of comments about how we might address these concerns. One is statistically a little bit more challenging, but conceptually, hopefully will help people see the issue, right? We might want to change the hypotheses. We could make the null hypothesis that there is a difference between the two samples, that the suspect is not, the suspect sample does not match the crime scene. That's my null hypothesis. And I believe that until I see enough evidence that they're so close, I should assume they did come from the same source. This does happen in other fields. In medicine, when someone has a drug, a COVID drug, say, and they show that it works, after a certain number of years, you're allowed to have generic drugs, right? What they do when a pharmaceutical company comes up with a generic is they do a test of this sort. They say, I'm going to start by assuming the generic does not match the known drug, and the test must prove to me that it does. And so this is sometimes known as equivalence testing for that reason. I'll stop there. So I'm going to go on stage 2. Before I do that, I'm going to answer a couple of questions. M. Eggert says, is the binary threshold based on how many false negatives you are willing to accept for every false positive? Yes, that is exactly the way of thinking about this. You can think about it in those terms, or just what are the two rates and how do I want to deal with those? And just to touch base on an earlier question, Marissa asked about inconclusives. If you don't have enough information, how can you not make it inconclusive? Absolutely. Inconclusives come up for a lot of reasons, a lot of valid reasons. Sometimes the evidence is not sufficient. It's too short a recording. It's too blurry a fingerprint. No one's saying that inconclusives are not ever the correct answer. We just want to make sure we know that people are doing it appropriately. And there's a reference provided in the Q&A to a paper by E.T.L. Jour about inconclusives that maybe we can, I'm not sure how we'll get that out to you. Stage 2, I want to move on to stage 2. So let's assume that we did the first stage. We found the samples to be indistinguishable. We could not reject a null hypothesis. We've already identified there are concerns with that piece of the story, but for the moment, let's leave it be. We have these quote unquote matching samples. Stage 2 says important to identify how likely that conclusion is by chance. Could this just be a coincidental match? Right? One of the anecdotes I tell sometimes people to get this is from the movie The Fugitive, where again, there was kind of an eyewitness report by the wrongfully accused husband that there was someone else in the room and it was a one-armed man. And, if you go out and you find a suspect, there's obviously a big difference by saying the witness said it was a one-armed man and the suspect matches that description, than if the witness said it was a two-armed man and you found a suspect that matches a two-armed man, right? So that's an extreme version of this. So stage 2 information, unfortunately, for example, there is a glass standard for how one measures glass and determines whether two samples are indistinguishable, but it stops at that point, and it doesn't suggest the need for a stage 2, and that's always bothered me a little bit. So let's talk a little bit about stage 2. In some scenarios, stage 2 is relatively straightforward. Blood type, DNA, paternity suits, those kinds of things. What we usually say is the putative father matches, and we can tell you how likely it is that they match by chance. So those kinds of probabilities, in those settings it has been done. Where it is rare is with continuous data. And so the figure here is supposed to show how we might think about this. So these are measurements of the refractive index of glass for samples from different windows. And so you can see this population has a range of measurements. And let's just suppose we have a control sample that has a mean where the red line is. So that came from the crime scene window. To answer the stage 2 question, how likely is it that my test will conclude indistinguishable? What we really want to be able to do is say, oh, this is the population of glass in the world. A lot of glass samples are between 1.515 and 1.520. See all of those samples. If that were the truth, how likely would it be to get a match? And then we would move over a little bit and we'd say, oh, there's some that are near 1.52. If that were the truth, how likely is it that I would, just by chance, get samples that are close to matching? And then, of course, there are some over here, and for these, it may be, we might decide it's quite likely that they'll be indistinguishable. So that's the stage 2 argument conceptually. And here's how I think about it. Suppose we have a control sample, aluminum concentration, in this case, slightly different than the picture I just showed you, where the mean is 0.73 parts per million, or whatever it's measured in. And I'm going to do a statistical test. right? We spent some time last week learning about it, reviewed very quickly today. I have a procedure that I can pull off the shelf and use to compare two sets of fragments. And to illustrate how stage 2 might work, I'm going to make a very incorrect, simple assumption. Suppose there are only 3 types of glass in the entire world. There are one type of glass happens to match my window at the crime scene. That is, these are sources that have true mean equal to 0.73. For any such source, when I take a sample of fragments from it and I compare it to the control sample, it's very likely that I'm going to be fine that they can't be distinguished because they did in fact come from glass with the same exact mean. And so we might say, well, if they match, those two types of samples will match almost all the time, say 95% of the time. But then the second bullet says, okay, there's another type of glass. This type of glass has aluminum equal to 0.78 on average, but of course there's some variability when I take measurements. And so if I take a sample from this source, truth equal 0.78, and compare it to this other sample, where truth equal 0.73, turns out there's some probability that these two will be found to overlap and will be, in this case, incorrectly found to be the same source. And for the numbers I've chosen, it turns out that's about a 50% chance. And in this simple world, the third type of glass has very high aluminum concentration, 0.83. It's very different. And for 5 fragments from this sample population, it would be very unlikely to find 5 fragments from a 0.83 type of glass and 5 fragments from a 0.73 type of glass and decide that you can't distinguish. That would only happen about 2% of the time. And so that's how I think about stage 2. And to really do stage 2, you need to know how much of the world is 0.73 glass, how much is 0.78 glass, how much is 0.83 glass. So that's how we think about stage 2. Of course, that's a simplified version of the world. In fact, there are many, many types of glass. And the stage 2 coincidence probability depends on how many types of glass and how different they are. The key thing for you to know is what impacts the probability of a coincidental match. As we just saw, we get a coincidental match if the control sample and the random population of samples are similar. So the control sample is very ordinary, like the 2-armed man or the white car. We get a high coincidental match if the population is variable and there's just many, many types of, much variability in glass sources. And also a lot of variation. So there's many, many types of glass. We might then still find a high coincidental match. So what does this mean to us as glass examiners? It's hard to do the calculation, but it tells us when we should think about the match, the conclusion we're seeing indistinguishable as being of high probative value. So here are a couple of questions to finish us up for stage 1. The first question asks about the first stage. And it asks about a question that you've asked a couple of times. What should we do about the cutoff? And I want to get your opinion. So there are multiple choices here. You can read through them. We'll give you a little bit of time. Anthony, you'll give everyone a warning, correct?
About 37% voted so far.
Great.
All right, we'll give you about 10 more seconds.
Drum roll. Great. Thank you, those who have participated. I need to kind of look at the numbers. So relatively few people chose 1, 4, 1, 3, and 4, and more people chose 2, and a lot of people chose 5. And just to repeat those, choosing a cutoff that's high or low has the obvious challenges of, if we pick a really high cutoff, we'll never eliminate anyone in the case of the glass. If we pick a low cutoff, we'll always eliminate the suspect, and so the glass evidence won't have value, so those are not too helpful. Number 3, of course, would be perfect if only it could be done, but it's not generally possible to choose a cutoff so that there are no type 1 or type 2 errors unless you had two types of glass that were so far apart that they never overlapped or something like that. And as I mentioned earlier, society really needs to make the choice. And of course, we all realize by the end of this conversation that figuring out where to put the cutoff is actually a challenging problem when there is the opportunity for error. And the statisticians tend to think that's pretty much always the case. So cutoff is hard. And then here's a second question about stage 2.
We'll go with about 15 seconds.
Great, thank you, Anthony. So people like 1 and 3 and not 2, 4, and 5. So let's review those. Excellent. Which of the following statements are true? Stage 2 is very important because we need to know how unusual it is to find indistinguishable samples. That is, in my opinion, correct, and all of you agree. Stage 2, not very important because once you have a match, that's all you need to know. And that is obviously not correct. Stage 2 is difficult because the relevant population can be A, hard to define, and B, can differ from case to case. So really well done on that question. As we get to the end of the course, we begin to get a little bit loopy. So I ask if you're tired of this type of question. So let me summarize what we discovered about stage 2, the 2-stage approach, sorry. The first stage, in this case, determines if the known and unknown samples appear to quote unquote match or be indistinguishable. And the key takeaways for me are, if we use a statistical test, it should really say that. If we use a statistical test to make that determination, we should recognize that that test is assuming the null hypothesis is true and is therefore prejudiced, if you will accept that term, in favor of the null hypothesis. And that it's important to design that first stage with an appropriate threshold and recognizing that that's a challenging question. The second stage attempts to quantify what I would call the probability of a coincidental match. And so that requires careful consideration of the relevant population, as we saw, can be very difficult to compute. But as we all agree, we need to do it either implicitly, that is, in concept, be able to talk about how unusual a match is, or a determination of indistinguishability, or we need to be able to do some kind of explicit data collection and calculation to get at that. So doing a pretty good job of staying on time. And I wanted to make sure to leave enough time to talk about the piece that many people report finding challenging to stay with. So I'm going to spend the rest of our time talking about the likelihood ratio approach. We can think about the goal of the forensic evidence analysis process as being for the trier of fact, typically the jury, to make a decision about which of two hypotheses is best supported by the evidence. Same source or different source, if we're talking about the evidence, guilty or innocent in aggregate. But for our conversations, we'll be talking about same or different source as being the two hypotheses. To many people, not all, but to me and others, this suggests, thinking about things in what one might call a Bayesian way, for those who are here for the first week. And what that Bayes approach does is it tells us to think about probability. And probability shows up here in two different ways. And so rather than relying on the words on this slide, I'll go to this second slide, which lays things out with a little bit of mathematical notation, which I know everyone doesn't love. So let's remember, E is evidence and S is hypothesis or proposition. So we have evidence E, we'll think about this as the measurements, and S means same source. S with a bar over it on the slide means different source. And there's a mathematical result that we saw 3 weeks ago called Bayes' theorem. And Bayes' theorem can be written in the way that you see here. And we talked about this 3 weeks ago, but it's really important to review and go over again. The way that this particular formula is interpreted is you can think about it as having three ratios. A ratio is one number divided by another. The first ratio on the far right, where my cursor is moving, is the ratio of what we would call the prior probability of same source divided by the prior probability of different source. This is, what is the frequency in the world of same source comparisons or the frequency of different source comparisons? That's, I'm tempted to say two things. One, indisputably, that's a very hard thing to think right? The second statement may be not true, but you could argue it's impossible to know, right? It depends on other things, right? It depends on what kinds of cases are being brought to court, right? You don't control that. You just get to see the evidence. So that's sometimes known as the prior odds. Odds are ratios of probabilities. And the left-hand side, I'm going to skip to for now. Remember how we read conditional probability. It says, given the evidence, let me only consider cases which have evidence exactly like this. What's the probability that these two samples came from the same source? And what's the probability that came from different sources? And what's that ratio? So those would be, I would argue, this is what everyone wants to know. What are the odds that this evidence came from the same source based on the measurements I see? There is no argument that everyone wants that. The argument arises because you can't get that. What this formula says is you can get the posterior odds only in one way, and it's by starting with prior odds and then looking at the evidence. That was not the clearest description ever. I apologize. The middle term is what we're going to focus on. The middle term is known as the likelihood ratio, and it answers the question, how likely are we to see evidence like this, given that these are same source samples? And that gets divided by how likely are we to see evidence like this if these are different source samples. So I use the phrase often in the next 50 minutes, evidence like this. What do I mean? I mean, I have two footprints impressions, and they appear to be the same make of shoe and the same size of shoe, and they have 4 racks in common, and they have similar level of wear. Let's call that the evidence E. So I'm going to say, oh, what's the probability of seeing same make, same size, same level of wear, 4 matching racks, if I'm looking only at same source pairs of impressions? That's the numerator. The denominator says, what's the probability of seeing same manufacturer, same size, same wear, 4 matching racks, if I'm looking only at different source impressions? So that's what the likelihood ratio is. And this Bayes formula tells us how we can combine these information. Prior information, information in the evidence gives us updated posterior information. So the likelihood ratio is not something new. One point I like to make on this slide. The likelihood ratio is not new and different. It's used all over statistics in a lot of different ways. It is used in medical diagnostic tests. So it's a very common way of thinking about evidence. I also note here that the European entity guideline likes the likelihood ratio. I've said this already. This is what the likelihood ratio is. You'll notice the likelihood ratio is assigning probabilities to seeing evidence like this. It is saying nothing directly about the probability of it being the same source. It's the probability of the evidence that's critical. If you want to talk about the probability of same source or different source, as we saw over here, we'd like to do that. It's tempting, but what the formula says is the only way you can do that is by taking the likelihood ratio, which summarizes the evidence, and adding prior information from some other source. And I would argue that is not the role of the forensic examiner. A couple of more comments about the likelihood ratio in concept before we talk about how it might be used. The numerator assumes same source and asks about the likelihood of the evidence. It's somewhat similar to stage 1 in the 2-stage procedure, which also assumes common source and tries to assess whether we can distinguish or not. The big change is the likelihood ratio gives you an assessment of the likelihood of seeing the evidence. It does not make a binary decision of match, non-match. I like that. It's a quantitative measure, if you will, of how much these observations, quote unquote, support the same source hypothesis. That is, these types of observations would be expected under the same source. So that's the numerator. The denominator, the likelihood of seeing evidence by coincidence. So it's just like stage 2 of the 2-stage procedure. We are trying to figure out what's the probability that we would see evidence like this by coincidence. And here too, it's not a binary match. It's just saying, what's the probability we'd see similar evidence in a different source comparison? This slide has a few technicalities, which is my way of saying there are things that statisticians, if they're listening in, would be concerned about that I don't believe practitioners need to be concerned about, but I want to cover myself. So this is somewhat analogous to, quote unquote, the fine print, or the, yes, I read that before I downloaded the app, right? Okay. The things I'll mention here are the term likelihood is used because it's not always a probability. When you talk about continuous measurements, it doesn't make sense to talk about the probability of observing an aluminum concentration of 0.73426, right? Because you might have seen 0.73427. There are too many possible values to talk about probability, so we use the term likelihood. And a couple of other technicalities here. One is the Bayes factor and likelihood ratio are two very closely related terms that statisticians get very, very, what's the right way to say this? Religious about. So some people strongly feel it's the Bayes factor, others the likelihood ratio, but my perspective is those technical differences that statisticians are worried about are not essential for all of you practitioners to understand. So I'll leave it at that. You should know there's some nuance to this, but what I can describe, I believe, in fairly straightforward terms, things that everyone would kind of agree with in the statistical world. So what my plan is to go through the likelihood ratio approach by thinking about 3 different cases. But before I do that, I want to say a couple of things that we should know. In particular, the middle of the slide says how you talk about likelihood ratios. What the likelihood ratio statement is that the evidence like this, or this evidence, or this level of agreement of the evidence is 1,000 times more likely if the objects have the same source than if the objects have different sources, right? So there are 2 samples being considered. And the likelihood ratio allows us to say if the likelihood ratio is 1,000, it says this type of evidence, this degree of matching evidence is 1,000 times more likely under same source than under different source. So there's still the question of how to interpret it. And that is a place where there are lots of articles in the statistics world or the European standard where people generally say likelihood ratios of 10 are supportive, but likelihoods of 100 are more supportive, and likelihoods of 1,000 are even more supportive. So it's a continuous scale, which is something I like. Likelihood ratios less than 1 have a similar interpretation. So 1 over 1,000 is similar strength to 1,000, but it actually favors the denominator hypothesis. There's frequent reminders in today's presentation about the difference between making probability statements about the evidence, which the likelihood ratio does, and making statements about the hypotheses, which happens all too often. So here we go, a series of examples. The first is a very, very simple example to reinforce the concept. Let's suppose we're talking about blood type. There's a crime scene sample and a suspect sample. In this case, the suspect sample is known. I take a blood sample from someone, I compute their blood type. And the crime scene sample is an unknown. I don't know who left it. And suppose they both turn out to be type O. If they don't match, it's relatively straightforward in this case that we would say the suspect is not the person who left the blood sample. So let's assume they do match. They're both type O. The likelihood ratio in this case asks the question, what's the probability of seeing O at the crime scene, given that the suspect is O and it's the same source? Well, we'd expect that to be 1, right? That is, the only reason they wouldn't match if it is the same source is if there was some kind of lab foul-up, right? Which we hope is and expect to be rare. The denominator is the coincidental match. It says these 2 blood samples came from different sources, but they both happen to be type O. And we can ask that probability. And O, it turns out, is relatively common. So it's quite likely, 44% chance, that we would see O at the crime scene, that the suspect who left the blood at the crime scene is type O, even though it's not the suspect. And the likelihood ratio is the ratio of those 2 probabilities, in this case 2.3, and we would say the evidence provides weak support for the same source hypothesis. Notice that the answer depends on the specific blood type. So knowing that 2 blood type matches doesn't tell you how strong the evidence is. You need to know what they match on. If they matched on AB, a relatively rare blood type, the evidence would be more powerful. So I have 3 cases, which I sometimes call the good, the bad, and the ugly. The first case is, where do likelihood ratios work? And the answer is, we know they are being successfully used in single source DNA and also in simple mixtures. A DNA profile is a little bit like a blood type. At a location along the genome, we find out what alleles you have, and the alleles are usually recorded as numbers that correspond somewhat to the length of a particular biological sequence. And so here's a particular marker known as THO1, and at that marker, humans can either have a 4, a 5, a 6, a 7, an 8, a 9, a 9.3, a 10, or 11. And humans have 2 because they get one from their mom and one from their dad. And so you can imagine having a blood sample at a crime scene, doing a DNA analysis, and finding out that the alleles at location TH01 are 7 and 9. And then you find a suspect, and they also show a 7 and a 9. It turns out, just like for a blood type, we can do a simple probability calculation. Okay, maybe not so simple in this case, to say what's the probability that these 2 individuals would agree on blood type if they are if it is the same source, so they are the same person. We would again expect that to be 1, but we can ask what's the probability that they'll match on TH01. They'll both be 7 and 9 if they're different people. And I won't go through it in detail, but this is a known biology calculation. The probability of a coincidental match in this case is about 0.06, and the likely ratio is 1 over 0.06 is 15. So just a match on this one genetic location gives you a likely ratio of 15, considerably stronger than the blood type we saw. The reason the likely ratio is talked about so much and used for DNA is because we can do this at more than one location along the genome. Before 2017, the CODIS database had 13 locations. Each was on a different chromosome. And that means they could be treated as independent pieces of evidence. And 3 weeks ago, when we talked about probability, we found that if events are independent, their probabilities can be multiplied, which means their likely ratios can be multiplied. And that means if I find 2 blood samples match on 13 different DNA locations, you might have 15 times 15. They're not all going to be 15. Maybe one is 5 and one is 35. You multiply all those together, you end up with some very big numbers. Very big numbers, okay? And those are addressing coincidental match. James notes in the Q&A session to me, the one thing that DNA needs to be worked on carefully is twins or other relatives need to be accounted for separately. I'm not going to discuss that as much, but that is a situation that generally gets, a question that generally gets raised when we talk about DNA. So it's worth taking stock about why the DNA, why it worked here. One is it required knowing a lot about biology. 2, it required that the biology, in this case that we do understand, ends up giving us a model that allows us to get the probability of a coincidental match. We're going to see that that's harder in other places. And there are good databases about allele frequencies available. And this DNA work has been done, developed, and tested in the scientific community. That having been said, even DNA is not perfect. There are errors that come up. There are lab errors. Mixtures are very complicated and are not yet at the same level of accuracy as ordinary single sample comparisons. But it shows us the pathway. So I'm going to talk about, that was the good. This is the bad. That is, it could work in trace evidence, and people are trying to make it work, but it is hard, and we'll see why. Okay, I'm thinking about glass and bullet lead here, where we have chemical measurements. We can think about a likelihood ratio for this type of evidence. Why do I say that? Here's a picture that lets me think about why it might be able to work. There are 2 pictures here. One is the measurements of refractive index for, I think it's 44 measurements or maybe 49 measurements, 49 different fragments from the same source. So this is what I call within source variation. There are 49 different fragments. They have different measurements, but they're all remarkably similar. Look at the scale. The right-hand side is a picture we've already seen once today. These are different glass sources. And so being able to say, how much variation would we expect if different sources on the right, how much variation from the same source on the left, the fact that these are different, and I'm going to show you how different they are by putting them on the same scale. So now they're on the same exact scale. You can see there's much less variation within the source, different fragments, than across different sources. And M. Eggert asked, how do the numerator and denominator relate to within and between? And you were ahead of me. That's exactly what I'm going to say, is under the likelihood ratio says, let's suppose we have X and Y, measurements of refractive index from the crime scene sample X and the unknown sample Y, the subject sample Y. And suppose we think about those continuous measurements and want to assess the similarity. Under the same source hypothesis, we have two sets of measurements from within a single source, and therefore the within distribution that I just showed you is relevant. If I have measurements from different fragments that are all over the place, they're not going to be consistent with that within histogram. Under the different source hypothesis, I have fragments from different sources, and the between is the relevant piece. In fact, when you have different sources, you get both between variation and within variation. But as we see here, between variation is much, much larger than within variation. So that's exactly what the likelihood ratio tries to do. It asks, are the measurements I'm seeing the type of variation I would expect from two same source measurements? Or is it the type of variation I'd expect to see from two different source measurements? And this has been done. There are papers written about glass evidence. And the key finding is basically you get a small likelihood ratio if Y and X are different. They're distinguishable, as we would expect. We get a big likelihood ratio if Y and X are similar, but they're similar on an unusual value. And what Aiken and Lucy showed when they did some examples based on glass is likelihood ratio of glass evidence appears to be in the order of hundreds or thousands, where DNA evidence sometimes shows up as millions or billions. So possible, still not very well done. Possible because we have a well-defined set of measurements. We can think about building probability models to describe the variation. We might say measurements are normally distributed. That is maybe true on the left, not really true on the right, but something you don't need to worry about. Statisticians can come up with other ways to represent those distributions and to give them probabilities. Whoops, should be on this slide. So this canon has been done. I was involved in a project 20 years ago that tried to do this for bullet lead. When we did it there, we found a very strong possibility of coincidental matches, so that the evidence likelihood ratio is only 2 or 3 for some of the examples. And as many of you know, bullet lead is no longer used. There are challenges here, and we'll come back to these, but the stage 2 question lives here too. The denominator requires us to say, what's the probability of seeing same source, similar measurements if they come from different sources? It requires you know something about the population. And as we've said a couple of times already today, that can be a challenge. So I said the good, the bad, and the ugly. The good being DNA, where for single source DNA, we know how to do it. The bad, quote unquote, being the glass evidence, where we're not quite ready, but we think we might get there. And that brings us to, unfortunately, the one that most of us are most interested in, which is pattern evidence. So how might it work for pattern evidence? In pattern evidence, we have the same question, same source, different source. We have a lot of examples. The challenge, though, is what the data look like. The data in most of these settings is image data. We have a latent print on the left and a known print on the right, or a latent impression, a crime scene impression on the right, and a known shoe on the left from which we can make a test impression. Those are the comparisons. So that doesn't look like a histogram of measurements, does it? So likelihood ratios are going to be more challenging for pattern evidence. Why? the data that we are working from starts off at a very high level of complexity, a very high mathematical dimension. That latent print is a gray image with maybe thousands of pixels, and each pixel having a gray level. Very complicated data. Very hard to describe the probability of seeing an image like that. And so we often then resort to looking at features of those images, things like minutiae in fingerprints, racks in footwear, specific characteristics of bloodstain patterns. And the evidence E, in this case, is tricky to define. At one level, we know what E is. It's the two images. At another level, E could be a set of similarities and differences that I've observed. I will jump a little bit back and forth between those. But the likelihood ratio framework doesn't change. We know exactly what we want to do. We want to be able to say, what's the probability of seeing this set of similarities and differences, these images, if the two images came from the same source? And that's the numerator. And the denominator is, what is the probability of seeing this degree of matching features if they came from different sources, the so-called coincidental match. So how do you measure the probability of evidence given same source and the probability of evidence given different source? This is a very hard problem. If you want to think about it the way we thought about it for the first two examples, DNA and glass, the analogous thing would be to say, I just need to be able to write down the probability of every possible pair of images. Well, that's not possible. Or of every possible set of minutiae. That's not possible. One anecdote I always tell here is I read something somewhere, I have never been able to find it again, in which someone was talking about how to do likelihood ratios for handwriting or signatures. And they said, to illustrate, I might look at two signatures, a known and a question, and decide that the probability of seeing these two signatures, this degree of similarity, if they're same source, is 0.9. And my head almost exploded because I'm like, what does that mean? What does the other 10% of the probability go to, right? There's a virtual infinity of possible signatures. How do we assign the 10% probability to those? It's a very hard question to wrap your head around. So what I wanted to do is tell you how people who are thinking about it are thinking about it. So one example, Cedric Newman, latent print researcher, over the years has done a variety of things. The picture here comes from his 2015 paper, where he identifies minutiae. In this picture, there are 7 minutiae. And what he measures for each one is the location and the direction. The tail is identifying the direction of the ridge, and the type. And then he also is trying to come up with a way to characterize the constellation, the dependence among the 7. And so he gets for each of the 7 a set of features. And I'm not going to go through A, B, C, D, and E. But so 7 minutiae in his approach leads to like 21 measurements. And then you can think about trying to say, how do I assign probability of seeing, you know, these 2 sets of minutiae, one on the suspect print and one on the known print. So that's what it would, that's the closest one can think about really trying to assign probabilities. That's hard. So a lot of people are doing what are called score-based likelihood ratios. And I'll tell you about that in a second. And some people are arguing for so-called subjective likelihood ratios. Whoops. I'm going to start with the subjective likelihood ratios. The Europeans have, as you know, officially endorsed likelihood ratios. I'm not going to go through in detail what they say. They like them. I draw your attention to the last bullet, the last major bullet here, which according to their guideline says, ideally the probabilities would like to would come from data, as we did with DNA and glass, but sometimes experience and subjective assessments are okay. Most people in the US who talk about likelihood ratios find subjective likelihood ratios a little bit frightening. So I won't say more about it other than to say some people think that's a way to go. The European guideline also provides a verbal equivalence to likelihood ratios, which you can see here. Again, good to know, not something we can talk about in more detail. So I do want to talk in a little bit more detail about the idea of a score-based likelihood ratio. Because likelihood ratios are so challenging, what a lot of people have done is gone back to those two images that I started with and come up with a single summary score that measures either the similarity or the difference. I'm going to show you for a quote unquote difference score. So let's compute a difference score, D, for two images. You can think about putting one image on top of the other and subtracting them. And that's the difference, right? And what we would want to do in this case is maybe say, let's collect data. Here's the black curve here shows the different scores for sets of images that come from known same source pairs. Notice that the different scores tend to be low. They tend to be between 0 and 10, most of them. There are some different scores out here at 20 and 30. Very rare to see one out here at 100. And then we would do the same thing for the non-matches. We would get some sets of images where we know they come from different figures. And we would compute the different scores for those, and we would say that they tend to yield large different scores, around 40, most of them between 20 and 60. And then if we had a particular case that we were working on, we would compute the difference score. And we would say, oh, for this difference score, which looks to be about 10 here, how likely is that difference score if I had known matches? That's the height of the black curve. How likely is that score if I have the non-matches? That's the red curve. And I could take the ratio of those two, and that would give me a score-based likelihood ratio. So that's one way people are attacking this. It's somewhat controversial. Why is it controversial? One issue that comes up is there a single non-match score distribution, right? If I'm doing latent prints and I want to say, what's the likelihood of getting non-match score difference that like the one I saw? Maybe it depends on the substrate. I'm going to show you in a second. Maybe it depends on the number of minutiae. Should we let that happen? How do we decide what characteristics are fair? Here's an example published by Henry Swafford, who has developed an approach that we can think about score-based. Not exactly a score-based likelihood ratio, but it's very similar, in a program called FR-Stats. And what I've done is I've shown here the picture that I just showed conceptually for his work. He's got a similarity score. So the light shade here are similar, same source pairs, and the dark are different source pairs. And what I've done is I've done it separately for sets of images with different numbers of minutiae marked. So we can start at the bottom maybe. If you have 15 minutiae marked and you compute Henry's FR-Stat score, what you find is same source pairs typically lead to a score, in the 50s, 60s, or 70s, and different source pairs lead to a score in the negative 70s, and there's great separation. But now look up here at 5 minutiae. If you take a print which for whatever reason only yielded 5 minutiae, you can see that the same source, not quite the same, but very similar, scores between 0 and 75, but the different source pairs are now closer to 0, and there's much greater overlap. So here's a case where, and this often happens, the same source distribution is pretty common for the score, but the different source varies a lot, and it varies in ways that we may want to pay attention to. And so in this case, I would argue strongly that if you're going to do something based on a score, you need to condition on or think about or build separate approaches for different numbers of minutiae. The thing we don't know about FR stats is, do we need to worry about the physical size of the impression that we were able to lift? Does that matter? Should we compute different same source and different source distributions based on that? Or whether the piece we have is near the delta or not? These are the kind of questions you have to address before you can build a score-based likelihood ratio. Here's another example that's slightly different. It can be very hard to find a single score. And so here's another thing that some people are doing, and this is some colleagues of mine at CSAFE. They're looking at bullet lands here, and they have use a microscope, a 3D microscope, to get profiles of different bullet lands. And then they line them up as best they can. And they compute different summaries of these two curves. How similar are they? Do they have matching peaks here? Matching peaks here, for those who are interested, correspond essentially to consecutive matching stria. And so what they did is say, I can't find one good score, but I can find a bunch of scores, and that's what these 7 pictures are. They're hard to read, and I apologize for that. But the first one is consecutive matching stria. So the light blue are same source pairs, and the dark blue are non-matching pairs. And they have a variety of measures. I can't read them all, so I'm pretty sure you can't read them all. No one of them does a great job of distinguishing. But they asked the question is, could we put all 7 of these into a statistical approach and use that to distinguish? And they were able to do that. Again, this is a little jazzy. That is a little fancy statistics. They took those 7 measures as input, and they built a statistical machine, if you will. It's called a random forest, that spits out the predicted probability that these 2 lands came from the same bullet. And they used that as their summary score. And you can see that on the data that they were working with, it did a great job. The same source pairs using these 7 characteristics can be distinguished from the different source pairs. So really nice work. And I don't show it in this presentation. They've now been trying to test this on other data and doing reasonably well with it. So it does show some promise. So I'm going to try to finish up with a few discussions of concerns about likelihood ratios. First concern, originally put out by a couple of researchers at NIST, they noted that when you build a likelihood ratio, you need to build a model for the probability of seeing the evidence under the same source hypothesis and the probability of seeing the evidence under the different source hypothesis. I mentioned in talking about glass, maybe we think those measurements are normal. What Lund and Iyer did is they said, let's say we allow for all possible plausible models. So normal looks like it might work, but for those who know some statistics, the t distribution might work too. And gee, a gamma distribution could work also. Let's try all of them and see what happens. And what they found is summarized here in what they call the uncertainty pyramid. This is for one of their examples. They showed that if you assume that the distributions are normal, you get likelihood ratios, in the range of about 500 to 1,000. If you use a wider class where you assume maybe it's not normal, maybe it's one of those other distributions that I mentioned, but I'm willing to assume the measurement process has a symmetric distribution, so big and small measurements are equally likely, and I'm willing to assume that there's really a peak common measurement. That widens things, and they found the likelihood ratio could get to be as small as 100 and as big as 1,500 or something, right? But then look at the third line when they said, let's be as flexible as we can imagine being, and let's just assume we know there's a peak in the distribution, but we're not going to say anything else. So it can be a really strange distribution as long as it has a peak somewhere. And they found the likelihood ratio goes all over the place. So it could even flip below 1, which is very significant because above 1 it favors same source, below 1 it favors different source. And so they were very concerned that different assumptions about the model could lead to very different likely ratios. Very important point they made. My critique of their work is only that they were very generous in deciding what was plausible when they got this result. Lots of complications with the likely ratio. I'm sure that you feel that way already. Just one complication is my presentation, but I'm not talking about that. I'm talking about actually being able to do this. There are just so many issues that we've not even thought about yet, which is, how many sneakers might be out there? How long do they last? All of these things could be taken into account in the likelihood ratio. And so though I believe there is good work being done, it could be a while before likely ratios. And we need to remember, as Linda and I point out, that the likelihood ratio depends on different assumptions. So I have a couple more questions and then a few wrap-ups. So here's last 2 Zoom questions. I think there are 2. Test yourself first about the numerator of the likelihood ratio. What does the numerator of the likelihood ratio tell us? This turns out to be a good review. Anthony, I trust you to say when.
Just getting on to say we'll give it 10 seconds.
Great, thank you. Excellent. So here we are. First 2, everyone got right. This cannot be telling us the probability that the suspect committed the crime, because for one thing, it's only about this particular type of evidence. And 2, it's not the probability the expert was trying to confuse the jury. 3 is actually the correct answer in this case. It is the probability of observing the evidence like this, if 2 samples came from the same source. And we got 1/3 saying the 4th item. The 4th is the common confusion, the flipping of the 2 things. A probability statement needs to be very careful to find what population you are thinking about. In the numerator, we're thinking about same source pairs. And what you are assigning probability to. In the numerator, we're assigning to evidence. And so we are not talking about the probability that 2 samples came from the same source. We're talking about the probability of seeing evidence like this if they did come from the same source. But you get a second chance. Test yourself on the denominator.
This one seems to be easier. I'll give people 10 more seconds.
All right. Great, thank you all. So the first 2 were again intended to be easy no's for for the same reasons. One, the first one says it would talk about the probability the suspect did not commit the crime. In any circumstance, it only talks about this particular type of evidence, and that the evidence may be sufficiently different to convince us the person did not commit the crime, but we don't know that for sure. And it's definitely not the expert witness trying to confuse the jury. Once again, it is a statement about the probability of seeing evidence like this when I consider the set of cases that I've seen ever in my world where it's not the same source. So that's how I need to try and assess evidence, is think about all the cases I've ever worked where I knew for a fact it was not same source, and wonder if I ever saw evidence like this, right? That's the coincidence piece here. And once again, the no here is tries to put probability on being different sources, and we can't do that without having making some assumption before the evidence or using other evidence, which I don't think we want to do. So thank you for those who played along. It looks like I have one last question that I forgot, sorry. I promised this is the last one because we're on slide 82 of 86. This one's to have a little bit of fun with. Based on everything I've told you, what do you think about likelihood ratios? More than one answer is allowed.
Ten seconds remain.
And there we go. A lot of people like 1, 3, and 5. Okay. A small number of people like number 2. Number 1, likelihood ratios provide a continuous measure of the strength of the evidence. That is correct. That is what they try to do. Likelihood ratios are the greatest invention since sliced bread. I would think that I might be the one to say yes, but I'm not allowed to participate in the Zoom poll. So thank you to the 5 people who said that. Number 3, the likelihood ratio is intriguing, but seems very difficult to apply in practice. I think that's a reasonable statement. Only statisticians are interested in likelihood ratio. Thankfully, not all that many people said that. I fear that might be true sometimes. And likelihood ratios can be very sensitive to the assumptions made, which is true, and one of the other points I made. So if you have questions, put them in now because we're running out of time. I'm going to do a few wrap-up slides. I have wrap-ups specifically about the likelihood ratio because I know that that is one topic that people are really trying to get their grips on. What are the advantages? The advantages of the likelihood ratio, in my opinion, are it makes explicit the need for us to think about 2 competing hypotheses, the same source and the different source hypotheses. We must look at the evidence through both of those eyeglasses, if you will. It provides a quantitative summary, which I like, as opposed to the categorical non-ident. I like the strength of degrees. The assumptions that are being used can and should be made explicit. And so the likelihood ratio is tricky, but if it's done right, people say, I assumed this and this is what I got. If you don't like it, tell me what assumption you don't like and we can change it and see if it changes the answer. It's not a binary decision. It's a very flexible approach. It gets harder and harder to be flexible, but you could imagine trying to say, what's the probability of seeing both fingerprint evidence like this and shoe print evidence like this in a case, right? So you could have a likelihood ratio for both together. Very, very hard to do, but it's at least conceptually possible. But I am not naive. There are distributions, or not naive about this anyway. There are disadvantages to the likelihood. It requires these assumptions be made about the distribution of the evidence. As I said, if we're explicit about that, we can work around it, but those assumptions are troubling because, as we saw, the likelihood ratio can be sensitive. I've had an ongoing conversation with a statistical colleague who says, The problem with this likelihood ratio argument is in the US, there is no defense requirement to provide an alternative hypothesis. So they object to the likelihood ratio on the basis of who's making up the alternative hypothesis. And likelihood ratio, as we saw, requires some information about the population distribution. And they can be very confusing for people to hear. So here's my last slide, and then I'll take the remaining 3 to 4 minutes, or 3 minutes, 2 minutes, to answer a couple of comments that are in the box. I hope that I've convinced you over the last 3 sessions that, thinking about forensic evidence doesn't mean you need to know probability statistics and at the level of a statistician, but it does require we know the concepts. When we're assuming independence, what is a statistical test doing? So I've tried to review the basics, discussed how those basics inform things like black box studies, the 2-stage approach, and the likelihood ratio. My takeaway are the last 3 bullet points here. Any approach should account for the competing hypotheses. It's not okay to look at the evidence and just start going, yep, look same source, look same source, look same source, and not say, could it have happened by chance? Could they be different sources? That's number 1. Number 2, very important to explain what we're looking at, what features, what data we know we have or don't have about it, and why that leads us in a certain direction. And 3, always endeavor to try to put in a level of certainty. So let me make a few quick comments in response to what's popped up in the Q&A. Who would I credit to developing the likelihood ratio? As I said, the likelihood ratio for a variety of uses comes up in statistics, and I don't know that off the top of my head. I'd have to go back and look at it. There are a number of people. There's I.J. Good is one person. David Lindley is a statistician who framed statistical thinking about evidence. And again, not just evidence in forensics, but evidence of disease, right? In the same way. One compliment for me, thank you. And then Jenny mentions a couple of things. One about handwriting and trying to say, one of the things about handwriting is it's based on only considering natural variation and trying to judge whether 2 samples could be from the same person, taking that into account, and says that distinguishes it from all other pattern evidence. To me, that's a matter of degree rather than a binary thing that makes it different, right? So I don't know that I agree with that. I would say when we look at footwear, we're really trying to, judge similarities, quote unquote, not necessarily natural variation, but variation from a variety of sources. So I think of it as a matter of degree. And Jenny, and I apologize if I'm saying that wrong, also says, would I agree that forensic evidence is at best just supporting evidence, cannot be regarded as the lone standing evidence during judicial proceedings. Statistics can contribute significantly to the integrity of forensic evidence if we can bridge between the 2 sciences. Yeah, I mean, I think many of you know more than I do, and certainly any of the lawyers who've taken the workshop, there aren't many today, but we've had lawyers before, can talk about this. There are evidences in which forensic evidence seems to have played a large role in the decision outcome. We only know that by talking to the jury. So it's stronger if it's only the supporting evidence and there's other somewhat compelling evidence lining up. But almost every source of evidence, I was going to say shy of video of seeing the crime happen, but with the ability to generate deep fake videos, even that is not going to be certain anymore, has the same concern, right? Eyewitness evidence used to be thought of as the gold standard, and now we find out how poor memory is. Latent prints evidence, for years people testified, there are never errors. We know they're rare now, but they happen. So I think it's a healthy conversation to understand how to interpret the evidence, that errors occur, that it's okay. Please tell your friends. We will do this again. I also do it at the IAI meeting in person each year, and love to be able to engage with people more than we can do via Zoom. But thanks for being here.
Hal, I know I speak for all of us who have attended live and those who are watching the recordings when I say we truly appreciate the time and wisdom you've shared with us throughout this entire series. On behalf of everyone here at CSAFE, thank you all for joining us, and we hope you have a great day.